we've been now for a while at ETH, and we've benefited a lot from collaborations with quite a few people, and on the various topics that we work on, and the early parts of this project were actually worked on also by Peter Lee, who's now at Oxford, who's also in the audience, also Julien Basset, and Tobias Frey, who's now working at Bosch. Okay, so I acknowledge this support, and Peter will probably recognize some of these early measurements. Okay, so why would you bother putting circuit QED together with quantum dots? Why would you bother trying to integrate superconducting electronic circuits with semiconductor quantum dots? And there's maybe a number of motivations. Each one of these systems is quite nice to study quantum physics on its own. You can investigate spin qubits in semiconductor structures to try to build quantum computers, or just because you're interested in the quantum physics or the mesoscopic physics of these structures. It applies for superconducting circuits. Yeah, you could be interested in their quantum physics, doing interesting fundamental experiments or applied experiments. And so you wonder why to put these together. And so there could be, people could have various motivations. One of my personal motivations for doing this in our lab was, my personal expertise clearly came from this end of things, superconducting circuits. And my impression was that there's a lot of nice technology that has been developed for performing measurements on superconducting circuits that I thought could also be interesting to use in the context of semiconductor structures. And I hope that I can give you some ideas about why that is. So while many of you know about it, I think I still want to spend the first few minutes to give you a general idea of what is attractive about cavity QED in general, or circuit QED in particular. Yeah, so cavity QED is this field where you're trying to couple an individual two-level system to a mode of a radiation field that you confine inside a cavity made of high reflective mirrors, and you're trying to reach a regime where sort of the storage time of the photons in the cavity and the lifetime of the two-level system inside the cavity are large enough that the dynamics in the system is governed by the coherent exchange of excitations between the two-level system and the radiation field. And trying to reach this regime where losses from the cavity or losses from the two-level system are negligible. And then you can mostly think about it in terms of a coherent quantum mechanical system. And so this here's sort of the atomic physics depiction of it, with a mirror-based cavity and a two-level system, and an atom with a dipole moment. And if you're sort of working with electronic circuits like our lab does, so then you could just map this harmonic oscillator formed by the cavity and the two-level system given by the atom to this little electronic circuit here. So you use an LC oscillator that could be a coplanar waveguide oscillator, or really lumped element oscillator made from an inductor and a capacitor. And the way how you couple it to a quantum system of your choice, which could either be a superconducting qubit or a semiconductor quantum dot, is you're trying to just fabricate a large capacitor between the two. And if this capacitor is large enough, you should be able to make sure that the coherent interaction between photons living in this harmonic oscillator and excitations in this other quantum system that you're interested in are overwhelming any decohering effects like the losses that I've mentioned before. Okay, so what could this be good for? So first, it's good for isolating this quantum system, whatever it is, from its environment. So if this quantum system has microwave frequency transitions, then those could couple resonantly to the excitations of this harmonic oscillator here, and you can use the fact that you can tune the transition frequency of most of these quantum two-level systems like superconducting qubits or semiconductor quantum dots. You can tune their energy, and you can tune in and out of resonance with the superconducting cavity. And for example, when you take this two-level system here and you detune it from the cavity resonance frequency, you can essentially isolate this qubit from the vacuum fluctuations in its electromagnetic environment, and that allows you to increase the radiative lifetimes of these quantum systems. Yeah? Obviously, that is assuming that they don't couple strongly to something else that you don't control. So you can use this phenomena to improve coherences, and this can be done while you can still drive transitions in these two-level systems that you're interested in. You can also use a nice technique that's actually employed widely in superconducting versions of cavity QED. You can use a measurement of the transition frequency of this harmonic oscillator here to read out the quantum mechanical state of the two-level system. So you can use the resonator as a probe for the quantum system in a so-called dispersive measurement that you can employ when the two-level system is detuned from the resonator. And you can also couple, so you could imagine not only having a single quantum system coupled to the resonator here, but it could be multiple quantum systems, and then you could have qubits interact with each other. And that might be useful for building a quantum computer. And for example, one of the ideas why people are interested to take semiconductor quantum dots and spin qubits formed out of those and couple them to superconducting resonators is because that could solve the task of building a larger spin-based quantum computer where you can get delocalized coupling, or coupling that can be mediated over larger distances between individual quantum systems. And then what is also interesting is that you could, if you tune this quantum system on the right here into resonance with this resonator, you can control this coupling strength over time. You could actually convert an excitation that was made in the quantum system here into the photon in the resonator. And so that would allow you to, for example, send in a controlled way quantum information which is first localized, say, in a spin qubit, convert it into a photon in the resonator, and then release the photon from the resonator. You can send it somewhere else, and that you could use to entangle remote things with. And you could also use it for this experiment that I've mentioned to you, where you could just try to look at the radiation that this quantum system here emits into the cavity to learn something about it. Okay, so that's sort of generally why cavity QED is interesting, yeah? Or at least some of the reasons why it's interesting. And when you realize these cavity QED systems here with superconducting circuits, this also gets technically relatively straightforward. Yeah? What straightforward means is maybe a little bit a matter of taste, yeah, but you can use micro and nano fabrication techniques to integrate these two parts here on a chip and do an experiment, which probably in the end is a bit easier than placing atoms, have atoms fly through mirrors in a complicated vacuum apparatus, but it's probably a bit of a matter of taste. But I think the fact that you can easily work with these here has led to quite a success of doing cavity QED with superconducting circuits. So on the title slide, we've already seen another version of the picture of this. So circuit QED, cavity QED with circuits. One of the common versions that people employ and that we are discussing in this talk is to use for the cavity a coplanar waveguide resonator that you see here, whose length is a wavelength where you have a center conductor that's a few micron wide, that is separated by a little few micron wide gap from the ground planes, and where the length of the center conductor sets the resonance frequency, for example, for this lambda mode of this coplanar waveguide here, where you can then place the object of interest, if you want to come into the electric field, for example, into the center of this mode where the electric field is maximum. And so when you do this with superconducting circuits, it's kind of relatively easy to implement. You more or less get strong coupling for free, so you can coherently map excitations in this qubit to excitations in this cavity. And and at the same time, as I mentioned already, these systems are relatively easy to fabricate and to operate in your lab. So, for example, if you ask any optical or microwave cavity QED person, say, okay, could you envisage making 10 of your systems and doing something interesting with them? They will probably tell you, yes, they can envisage it, but it's going to be very hard. Yeah? So I think, for example, Serge Roche spent a good fraction of his career to get his very nice Rydberg atom 1 cavity experiment into a Rydberg atom 2 cavity experiment. Yeah? And, so it's a huge challenge for them, and also at optical frequencies, like in the Max Planck Institute for Quantum Optics in the Atlantis group, they now are able to couple systems with 2 cavities and 2 atoms, but going beyond that, it's more technically challenging than in the superconducting systems. Again, because it's so easy to fabricate, and then you get all these nice quantum features, quite a range of research directions has developed out of this. You can just do basic quantum optics experiments with quantum. Aspects of the circuit QED idea are used in quantum information processing with superconducting circuits quite widely, and there's all these hybrid quantum systems, or at least from the perspective of the person working on superconducting circuits, who call these hybrid quantum systems because they combine superconducting quantum circuits with something else, like in this case, semiconductor quantum. Okay, and then, by the way, I should encourage you to ask questions if you have any, and if anybody's interested to get a PDF copy of the slides, you can also ask me, and I can give you a copy anytime after this talk. Yes, I mentioned there's these 3 areas, basic quantum optics experiments with these circuits, quantum information processing applications, and hybrid quantum systems, and I just want to spend another few minutes briefly giving you an idea. So there's been really a nice range of very nice quantum optics experiments done with these superconducting circuits. I think by now you could probably write a nice quantum optics book, yeah, and not ever talk about atoms or experiments with atoms. I think all the fundamental experiments have been done with superconducting circuits, and I think all of them have been done at a similar, maybe at times nicer level of quality. If you look for textbook examples for phenomena in the interaction of light and matter, superconducting circuits can demonstrate those nicely. So there's these basic things like looking at a vacuum-Rabi mode splitting in a spectrum, to doing very fancy things like making cat states or superpositions of Fock states where you measure their Wigner functions. Where you can do nonlinear optics with photons, where you can look at squeezing and parametric amplification, which is something that I might mention a bit about. And where you can also use these strong interactions for not even, interactions can be so strong that you don't even need a cavity to have strong interactions between individual photons and individual two-level systems. You can just leave the cavity away and just put your qubits into an open waveguide and still see strong interactions. So that's a whole range of experiments. That is, this is only a small fraction of maybe those articles that were published in glossy journals with glossy covers. Yeah, there's many more, and maybe more interesting ones, and it's also not totally up to date anymore.
Sorry, just out of interest, so how large are these cat states that have been made?
Oh, okay, so that's a good question. So Jonathan Holm, who's an ion trap person at ETH, so he also makes cat states, and so there's a question who has the biggest cat currently, yeah, and then there's also a question, how do you measure the size of the cat, and one of the measures is kind of distance in phase space, which is not the same thing as the photon number, and I think in terms of distance in phase space, they can do cats which are the size of 100 photons or so, roughly on that order. And I think Jonathan Holm can do a bit larger ones, but his photon-like excitations are the phonons and the oscillations of an ion chain. Yeah, so on the order of 100, yeah, which then, actually, if you then translate that to a real photon number in the cavity, that's significantly smaller. Okay. Yeah, and then I said that there's, and certainly this quantum optics experiments is something that we like to do in our own lab. then these circuits get used a lot for quantum information processing. I think some aspects of it get used in sort of almost every superconducting circuit-based quantum information processing experiment. So all the Debye transfer criteria have been addressed in these circuits. Algorithms have been implemented, and currently I think what people are focusing most on is trying to build systems that are enabling error correction, and somewhat what many people think is a little bit of a holy grail is to make a circuit where error correction is implemented in such a way that you can keep a quantum state of a superconducting qubit preserved forever by actively running error correction on it. And so there's been nice results published last year, and many of the major groups working on this, they're trying to push this to the next level. So this was only implementing error correction partially, and not increasing the overall, or not increasing by enough the overall coherences of the effectively encoded qubits. But so here you will see more progress, and we've actually teamed up with, our own lab has teamed up with Leo Di Caro's lab in Delft, and a Swiss startup and the Dutch research organization to also try to contribute to this. So building a big quantum computer is difficult and will take a while, and so the question is, what do we do in between? So for example, one of the goals that we have in our project is to make a circuit first with 7 qubits and then with 17 qubits, just to make one error-corrected logical qubit. And the question is, that the most interesting thing that you could do with this complicated system that we've spent lots of time on developing? And many groups now think that on the way to it, you could actually use these circuits to do quantum simulation type of experiments. And there's some ideas that Andrew Howe formulated in this kind of outlook article, and you see more experiments coming out doing quantum simulation experiments with both digital and analog with the hardware that we have. And I think probably most people believe that the real interesting, sort of the work that is interesting to physicists in quantum computing with superconducting circuits, or probably with any near-term system, will be in this domain of quantum simulation, because it's likely that you can do interesting quantum simulation experiments with a reasonable amount of hardware, whereas kind of fault-tolerant quantum information processing will probably take a bit more time to be really possible. And it's probably also gonna move out of people's labs relatively quickly, because if you think about building a few hundreds or a few thousands or more qubits, that's probably going to be challenging for like a lab-based effort.
Yeah. A question about the previous slide. In the bottom right, is there like a proposal for a quantum error correcting code? Or
this year?
Yeah, it's
no, it's not. So okay, good. This clearly indicates that I don't say enough about these slides, okay, so this is just for giving you the overview. So that's an idea. So Andrew Howe had this idea that was inspired by, I think, by sort of atomic physics idea to make arrays of things, to make artificial structures. And these are actually resonators that are effectively ordered in a way that they form a Kagome lattice, which is also a lattice structure that appears in solid state. And his idea was to sort of look at the dynamics of photons in these complicated structures to understand something about Kagome-type lattices in solid-state systems. And so this is 3 by 3 centimeters, and it has probably around 100 or a few more resonators on it in the structure, and he's trying to look at the properties of these resonators for this purpose. So for example, to control the quantum state of each one of these resonators individually is hard, and the question is whether you can learn something by just looking at the global effects in the structure. In the end, something that you do in solid state physics. You don't need to look at every atom individually to know what your solid does. Okay, and so this presentation today is about hybrid systems, and also with superconducting circuits, and this is what we were talking about. And there's also nice experiments with NV centers, and Yasu has this presentation and their work on magnons, and so there's quite a range of work, also mechanical systems, and in our own lab, we have an experiment where we try to shoot Rydberg atoms across these superconducting resonators, which is actually also starting to produce some interesting results. Okay, so let's get back to the actual thing. I think I do need a little bit of water, so you can think about a question while I pick up a glass. There's a bottle up front, so. Okay, so good. So I gave you some of this background, and I personally find it pretty interesting. I think there's lots of activities in this general area, and so I think the prospects are good. And while one might have thought, okay, now there's quite a number of people working there, and you might wonder, okay, is it getting too squeezed in? Does everybody have the same idea? And just this morning at breakfast, Joran also said, hey, why don't you do our experiment that we've suggested? Yeah, and I think it's still in the situation that there's lots more suggestions than people can do actual good experiments on. Yeah? And so that's nice to see. So there's lots of room to do stuff that is interesting. And that was maybe not so obvious to see when this started. Okay, so I'll continue now exploring this quantum dots in superconducting cavities idea, and I see that I'm going a bit slowly looking at the time, but okay. So in this particular setting, as I mentioned, so you can realize interfaces between quantum systems. So one of the cool things that you could do, you could, for example, think about what would happen if you would have a superconducting qubit and a semiconducting qubit sharing the same cavity. Could that be useful for something? Swap quantum information between the two, or could you use the superconducting qubit to learn something about the semiconducting qubit? That could be interesting. You can use this isolation aspect of the cavity, which I think is also a good thing to pursue. You can achieve this long distance coupling by putting a quantum dot here and putting a quantum dot at the other end of this resonator somewhere down the chip. And I think our initial motivation, and which the talk will probably be mostly about, is the implementation of alternative measurement and readout schemes for semiconductor quantum structures. And as I mentioned, maybe the example that I'll give you, and maybe one of the outlooks that we have, is to kind of correlate charge transport in these semiconductor nanostructures with radiation emission from them, which is something that we can do in the circuit QED context. Okay, and so this motivates this experiment by Anna Stockklauser that I've mentioned, and in superconducting circuits, our own lab has done quite a bit of work in trying to characterize radiation emitted from superconducting structures using correlation function measurements. And I have one more of these sort of overview types of slides, and then I promise I go on to the real thing. So, so one of the experiments that our lab wanted to do is it wanted to ask this question: can you characterize quantum features of microwave radiation when it gets emitted from a circuit? So how would you do that? Yeah, sort of typical quantum optics experiments before cavity QED was done were of the sort: you have some source and you have a detector, and you're trying to learn something about the quantum properties of the radiation emitted from your source by detecting the radiation. And the question was, would that work with microwave frequencies as well? And at microwave frequencies, it wasn't at the time so obvious what you would need to do to, for example, measure a second-order correlation function of the radiation emitted from a quantum system. And we have, in our own lab and also in other labs, people have developed techniques to do that. And so this is an example from a second-order correlation function of a single photon microwave frequency source, where the source is pulsed. Yeah, so you see these peaks. So the second-order correlation function is an intensity correlation function. So you ask, okay, if you have intensity detected at some time t, equal to 0 here in the center, how likely is it to detect radiation at a later time t? And so here, and for example, if you have a beam splitter and a source, and you have a single photon source at the beam splitter, and if the single photon source makes single photons, you have 2 detectors. The single photon will only go into one of the detectors, and so the other detector will stay empty, and if you multiply the 2 intensities, you always get 0, and that's an indication of, for example, the single photon character of the radiation emitted by the source. And you can sort of expand these techniques to reconstruct Wigner functions of the radiation emitted from these structures. You can look at the correlations between the source of the radiation emission and the radiation itself. Yeah? So that's what I meant when I said, well, if you have the semiconductor nanostructure, you can measure its quantum state. You can also measure the quantum state of the radiation emitted from it. And if you can correlate the two, you can know how the physical process works that emits this that creates the radiation from the emission from the nanostructure. And you can do more fancy things like quantum experiments. And so this we've developed for a while, and we wanted to use it in other contexts, and in particular we're interested in this inelastic tuning processes in semiconductor structures. Okay, so let's look at the first sample that Peter Leek and Tobias Frey designed and made in our lab. So this I've explained on the title slide already. So this is overview of the superconducting waveguide resonator, and it has a double quantum dot installed in this area. So if you zoom in here, you see that the resonator has a little finger stretching out from it. There's gates at the bottom here that you can use to form the double dot. And if you then take an electron, so these are all optical microscopes, and then if you take a scanning electron microscope picture of this early device, you see that there's these gates coming from the bottom that stretch out, and there's one gate coming from the top, which comes from the resonator. And when you bias these gates here appropriately, you can form like little puddles of electrons forming a left quantum dot and a right quantum dot. And there's two-dimensional electron gas extending on the left and on the right here, and charges can tunnel sequentially through this double dot structure. Yeah? And so one of the ways how you could use this as a qubit, you could, for example, use the charge states of electrons in such a double dot as a qubit, where you could encode it in different ways, for example, with the charge being either on the left or on the right dot, different qubit states. Or you could work with spins in these dots as well. Okay, so the typical frequencies that we work with are gigahertz-ish, sort of what many people do is they work somewhere between 4 and 12 gigahertz, because that's where equipment is easily available. Okay, and so that was the first type of device that we looked at. And so here's a little circuit diagram of that. So there's just this double quantum dot, which probably many of you have seen here at the bottom with the left and the right dot, and tunable tunnel barriers, and tunable gate charges for each of the dots. And the right dot is coupled to the resonator through this lead here, which you see there, and then connect up here. And you can measure the properties of radiation transmitted through the resonator. And so that was our first type of device, and about the same time, a number of other groups looked into similar devices. So Takis Kontos group looked at nanotube devices, which are shown here at the bottom, which have sort of similar structure, but where the semiconductor nanostructure is based on the nanotube. There were also other experiments with two-dimensional electron gases, and there's Jason Pettar's experiments with indium arsenide nanowires. And so they were all sort of getting into that around the same time. And now there's probably about 10 or maybe even a few more groups in the world who work on things like that. And also experiments with graphene have been done. Okay, so let me briefly tell you what sort of then the basic measurement looks like. So the basic measurement here, if you wouldn't have the quantum dots in a cavity, one of the ways to do this basic measurement is to do a transport measurement from source to drain, and just look at how charges tunnel through this double dot, and the typical structure that you then see if you measure current, you see this honeycomb lattice structure. And this honeycomb lattice structure you can understand by understanding how the gate charges coupled to each individual dot, how the gates themselves have some cross coupling, so they are not only coupled to an individual dot, but also to the neighboring dot. And then you have to consider that there's a little bit of capacitance between the two dots as well. And then you get these honeycomb structures. And every one of these cells in the honeycombs you can assign with a certain number of electrons, n on the left dot and m on the right dot. And when you go from one honeycomb to the other, from one of these cells to the other, so you change the electron number in either one of the dots by one. Okay, and a typical transport measurement then. So for a transport measurement to work, you have to have the tunnel barriers between all of these things sort of open enough so that charges can actually move from source to the left dot to the right dot to the drain. So here these tunnel barriers are quite open, and you see what you see here is a plot of the current in femtoamps versus these gate charges, which change the number of electrons in the double dot, and if you put these dashed lines on it, you see the honeycomb structure. So that's sort of a typical charge transport measurement, where we're actually at these so-called triple points here. You see the maximum current flowing through the structure. There's also current flowing along the edges of these honeycombs. And initially, the experiments that we've done were done with semiconductor quantum dots in the many electron regime. So that's where n and m are both much larger than 10. So say they are between 10 and 100 or so. But nevertheless, the charging energy of these quantum dots is so large that the physics of the quantum dots, at least for the purpose of our experiments, is more or less single electron physics. Yeah, it's only the last electron which you've added gives rise to most of the characteristic features of the quantum dot. And I'll comment on that again a little bit later. That's because of this large charging energy, the large electrostatic energy of the individual electrons in these structures. And so that allows us to really think about this as if there's really individual electrons tunneling from the left to the right dot, and so to some degree you can consider a two-level approximation for this system. Okay, so you can wonder what happens in these different regions of this honeycomb diagram. So along such an edge of the honeycomb diagram, you have this co-tunneling process from the left feed into the left dot, non-resonantly through the right dot into the right lead, the reverse on this other edge of the honeycomb diagram. And these triple points are these special points where charges can tunnel resonantly through two intermediate states from the source to the drain, and that gives you the points where you get the largest current. And at any other spot, you don't get any current at all. Yeah? So for example, if you're in these cells here, current is blocked because there's no available states for transport through the double dot. And a similar thing is the case here on the line connecting two triple points. So now charges can tunnel between the left and the right dot, but they can't come out of the double dot. And so therefore there's no current transport here. Okay, and so now you can ask yourself, okay, if you stick such a thing into a superconducting cavity, what will you see? And the first experiment to do is you can put your double quantum dot into this blockaded region here, where no charges can move, and then you can measure the resonator spectrum that your dot is coupled to, and you see this resonance spectrum here. And then you can go to a different position, like for example on this line that connects to triple points, and you can see how your resonator responds, and you see a little frequency shift of the resonance frequency, and you also see that the amplitude got a little bit smaller, and you can not only measure transmission amplitude but also transmission phase.
So what is in the y-axis?
In this axis right here.
Yeah.
Ah, okay, sorry. Okay, I see it. So here's the units, and it's amplitude squared. It's the transmission amplitude. So you apply. Okay, good. That I should maybe have said. So what we do is we bias the semiconductor quantum dot at one position, at one set of gate voltages, and then we apply microwave frequencies to the resonator, and we measure the amplitude and the phase of the transmitted microwave. So and that's the amplitude squared, which is like the transmitted power. So you have a spectrum analyzer at the output, and you scan your input frequency, you measure how much power you detect on the output depending on the frequency, and you get a Lorentzian line with the maximum that identifies the maximum transmission. And you now look at this, how it changes depending on the bias of your semiconductor quantum. And then you can do this type of measurement and actually do it not only at these two different points, but do it at all the points in this diagram. And what this then looks like is something like that. And these were these early measurements that we did.
So the gate which couples capacity with the dot to the resonator, is it grounded actually on one side?
No.
Floating?
Yeah, okay, good. So the physical, okay, good. Here's how it's done. So the resonator itself, that should be floating in principle. Huh? At lambda half, it's floating, but it is connected through this little inductor to a bias point, which you could bias in principle. Huh? But this couples to a node, so at DC it's grounded, but at the AC frequency, at the resonator frequency, it's not grounded. At the AC, yeah, DC it's grounded, but at the AC frequency it's not grounded.
Okay.
And I guess you're worried because you could think that could charge up and do something weird to your quantum dot and would not be a controlled gate voltage on your quantum dot.
If it was floating, we had to see a difference from the number of electrons charging the quantum dot in principle. But you don't see this. That's why I had this question.
Maybe let's discuss it later a bit more. So one thing that is interesting, that if you now look at this, how the amplitude changes versus gate voltages, you see that you also get this honeycomb structure, but the places where you get signal are quite different. Yeah, I mean, it's because now you don't measure charge transport, but you essentially measure the polarizability of your semiconductor quantum dot. So the gate couples to the right quantum dot, and what you're sensitive for is the possibility of the charge tunneling between the left and the right quantum dot. Yeah? And so the interesting thing about it is this now does not rely on transport, so you don't need to get an electron from the source into the left dot, into the right dot, into the drain, but you can in principle switch off the source and drain and just look at charges moving from the left dot into the right dot and back and forth. And this can happen exactly on these lines that connect the two triple points. And that's where we see signal or changes in the amplitude. And similarly, if you look at the phase, we also see changes in the phase, so reconstructing these honeycomb diagrams. Okay, and so in this diagram, you can identify different directions. Yeah, so for example, this direction in this diagram detunes the levels in the left dot from the levels in the right dot. The direction orthogonal to it detunes both dots relative to the source and drain, and we call epsilon here. And then the third thing that we can change in our experiment is the tunnel coupling between the left and the right dot, and that would be tuning the energy difference between the symmetric and the antisymmetric superposition states of the two individual quantum dot charge states. And these are the three parameters that we look at in our experiment. Okay, and so I claimed there is a connection with cavity QED. So we were wondering, okay, what in this experiment is the connection with cavity QED? The way we chose how to analyze it, which is not maybe not the only way, is to just say, okay, this system, okay, we have this double quantum dot. It acts like a charge qubit. We have a resonator, which we quantize, and then there's this coupling, which we know from the James-Cumming simultaneum. And we analyzed our data in this way. And so what you would expect is if you have a resonance, so it's an energy level diagram versus detuning between the two dots, a cavity resonance frequency, and the energy difference between the left and the right dot. And when you tune the energy level difference through the cavity resonance frequency, and if everything was coherent, you would expect to see a vacuum-Rabi mode splitting at the position where the two systems are resonant with each other. And so here you would see a vacuum-Rabi mode splitting, and if, for example, and this point here is the tunnel coupling between the two quantum dots, which we can adjust in the experiment. And if we make that bigger, for example, if the tunnel coupling is so big that the transition frequency between the left and the right charge, or the transition frequency between the two charge states in the double dot, never becomes resonance with the cavity, then you see the interaction by a little shift in the resonance frequency of the cavity, and also by an equivalent shift of the resonance frequency of the double dot. Or we're sensitive to this one because we measure. Okay, and so then the first experiment, or that you want to then do is the question, can you see this vacuum-Rabi mode splitting here? And so if you do that with superconducting circuits, a nice vacuum-Rabi mode splitting would give you two nicely resolved lines which are split by the coupling strength between the two systems, which is what we're looking for, which we will clearly not see in our experiment. So that's the strong coupling limit of cavity QED. Then there's this bad or fast cavity limit where now the cavity line width is larger than the coupling strength is larger than the qubit line width. And in this case, you would see something that resembles an electromagnetically induced transparency picture, yeah, where you see a Lorentzian spectrum of the cavity with a dip in the center that comes from the interference of the two excited states decaying back to the ground state. Or if you in the weak coupling regime, if you measure the cavity spectrum, you actually, so here's the weak coupling regime where we artificially in a superconducting qubit decrease the coherence of our qubit to just look at what would happen to the spectrum. And this kind of sharp dip in the middle, which we have for low qubit decoherence, it vanishes if the qubit decoherence increases. And unfortunately, most of the experiments that we did with semiconductor quantum dots were in this weak coupling regime so far. And most of the experiments have stayed, maybe even all of the experiments have stayed so far in this weak coupling regime when you couple charge of the semiconductor quantum dot to the superconducting cavity. Okay, so how do you see that in the resonators? So here's a typical, so here's a diagram. Maybe I need to go back to this point. So we now look with some more care at the line that connects two triple points, and we tune the transition, we tune the detuning between the two qubits relative to each other. And so here's what we see, and this is the phase shift of the transmitted radiation as we tune the transition frequency between the two quantum dot states. And at these white lines, the quantum dot normally goes through resonance with the resonator, and in the red region, the phase gets shifted to positive value, and in blue, the phase gets shifted to negative values. And so if you plot, for example, frequency shift versus this detuning between the left and the right dot, which is on this axis here, you see this shift here that comes from the interaction of the double dot with the resonator. And similarly, you could look at how the transmission amplitude changes in these experiments. And so this you can then analyze in this James Cummings Hamiltonian model, and you can extract parameters. And what we found for these first experiments here is that we get quite strong coupling. We get G's of about 50 megahertz or so, which is large. Yeah. But also the dephasing rates, the charge dephasing rates in these quantum dots were enormous. Yeah, there were sort of many hundreds of megahertz, maybe even the gigahertz. So all this data here is in the weak coupling regime. We understand how strong the coupling is, but it's weakly coupled because of charge decoherence in these devices. And then we've looked at a number of things that could be the matter. So we thought, oh, is it due to the fact that there's many electrons in these dots? And we did experiments with single electrons in the dots where we've depleted the dots enough that we're really at the single electron level. But that didn't help. Yeah? So the coherence state is still in the weak coupling regime. And then we also played a little bit with materials, and we've improved. So by now we have devices where the dephasing rates are maybe a few hundred megahertz or so. So they're getting closer to the strong coupling limit, but they're not quite there yet. But they're getting closer. And so with one of these devices with less, and I'll skip through some of this. And so some of the devices, or one of the devices where this charge dephasing rate is now 200 megahertz, we then have used to do this radiation emission experiments. And that's this experiment by Anna Stocklauser, which I've mentioned to you, and I'll briefly explain the essence of it. So here's the device that was made for this purpose. looks very similar. It's on a different wafer. We've changed the gate geometry a little bit, which I think, or which we think is related to this improvement in dephasing time. But conceptually, the device is very, very similar. And so we could extract the device parameters from these experiments, and they were very similar, like to the early experiments with this improved charge coherence. And then the thing that we were really interested in is the following situation is, so here's again an energy level diagram for this double dot, the source, the drain, intermediate states. And we were interested in what happens when an electron tunnels from the source into the left dot, right dot, into the drain, and energy has to be relaxed. Yeah? For example, if we tunnel from this state to the other state, there's an energy mismatch. And the question is, where does that energy go? And we're trying to couple it into a resonator by looking at, or by providing this decay channel, by coupling the right dot to the resonator, and then trying to look at whether this tunneling process creates any radiation in the resonator. And so we could do that versus this bias parameters in the double dot and look at the emitted radiation. And what was important for that is to have good radiation detection mechanisms, because what we noticed is for every electron that tunnels, in our experiments we would only make a photon with a probability of roughly 10 to the minus 4. So, which one can wonder why that is. There's maybe some explanation for it, but per tunneling electron you get 10 to the minus 4 photons. And that required to be very sensitive in the measurement. And that for that we use these magic, okay, they're not magic, but they're these superconducting amplifiers, which can be quantum limited. And I had the intention to tell you a little bit about this superconducting amplifiers, and also mention to you how we operate them and how they could improve your experiment, but I'll probably not do that, but you can ask me later about it, and rather I'll show you some data on these radiation emission experiments. So here's our parametric amplifiers, and maybe I should also say that we've started, so these ones, like every experiment in our lab that we do that has a semiconductor amplifier, it now has a superconducting parametric amplifier also, because it improves the noise properties by somewhere between a factor of 10 and 100, and so all your experiments speed up by at least that factor. And if you want to have, if you do microwave frequency measurements, you should be using superconducting parametric amplifiers. And we've actually started to give them away to people who are interested. So if you're interested in using one of these, you could get in touch with us and see whether they are helpful for you. Okay, you can. So these can be quantum limited, and you can have gains up to gains at bandwidth that depend, or gains that depend on the bandwidth, but your gain can be a typical bandwidth of maybe a few megahertz or so. It can be 20 dB or higher. Maybe as a little advertisement, we have a project with these guys here, a Swiss sort of technology transfer project with an ETH startup. And so from this summer on, you can buy a little box to do circuit QED experiments a bit more easily. Good. So what is the experiment on this radiation emission that we did? And I have to wrap up. So here you see some finite bias triangles on these semiconductor quantum dots. These are two triple points, and around the triple points you see these finite bias triangles. And now we set ourselves on one of these bias points, and we look at the emitted radiation from the cavity. And so we do that without applying any signal to the cavity, and we just listen to it. Yeah? So there's current flowing through a double dot, there's electrons tunneling inelastically. These electrons create half transitions. The energy that they relax gets coupled into the resonator, and we look at the resonator whether we see something. And depending on the bias conditions, for example, if the bias is weak, we see a small amount of radiation coming out of the resonator. If the bias is different, we can see a larger amount of radiation coming out of the resonator. And the line width of this here is essentially the line width of the cavity, which was 3 megahertz, and then we can integrate that power that gets emitted and plot that power versus the bias conditions of the semiconductor quantum dot. And so this is sort of an important plot here. So what is shown is the current flowing through the double dot in this blue line, and the radiation power emitted into our resonator, and the current is shown in the electrons per microsecond, and the radiation emitted is shown in photons per microsecond. Yeah, and you see that there's this mismatch of roughly a factor of 10 to the 4 between the two, showing this small efficiency. And what is also interesting to see is that the radiation emitted has much more features in this detuning between the left and the right dot. And the dashed lines are those detunings where the energy difference between the states and the double dot is resonant with the cavity frequency, which happens around 5.9 gigahertz. And so you see that we get these two peaks. There's a big peak in forward direction and a smaller peak in backward direction. And we've tried to understand how that happens. So here the forward direction is on the right-hand side when the quantum dot is resonant with the cavity, and the backward direction is on the left-hand side. And we've tried to analyze how this radiation emission depends on the quantum dot parameters. And you can see when the tunnel coupling between the two quantum dots is weak, you only see the right peak. When the tunnel coupling gets larger, the left peak starts to grow, and when the tunnel coupling is too large, you see sort of only one drawing peak. And you can understand this emission process essentially in the following way. So there's a forward bias direction where you have hybridized charge states, where it is likely for an electron to tunnel from the source into the higher excited state, which is predominantly localized in the left dot, then relax within the dot to the ground state and tunnel out of it. And that creates then a photon which we can detect. And we can determine the rate at which it gets created. And the smaller peak here in the reverse bias direction comes from the fact that at this reverse bias, the electron distribution in the double dot has this other symmetry. The excited state has less occupation probability next to the source lead, and therefore has a lower probability to get occupied. That then relaxes, and again has a lower probability to tunnel out of the dot from this state, and therefore you get a smaller occupation and a smaller radiation. Okay, and then we've kind of looked further at that, and you can analyze the peak heights and intensities and these different peaks, and you can see what we learned from it. Okay, sorry for being a bit wrong in my planning of time. Probably spent too much time on it in the beginning of the introduction. Okay, so what is it that we did? So we developed this semiconductor quantum dot system, coupled it to a superconducting cavity. We can see sort of cavity QED-like physics, but in a regime where we don't have strong coupling, but weak coupling. Nevertheless, we could use these circuit QED techniques to read out double quantum dots in a different way, and the way is sort of a polarization measurement, not a charge measurement, not a transport measurement. And sort of in this last experiment that I've only briefly talked to you about, we have been able to look at the radiation emitted from inelastic tunneling processes in double quantum dots. And our hope is that in future experiments we can actually correlate the charge transport with the radiation emission and learn something about the mesoscopic physics of these processes in semiconductor nanostructures. And clearly one thing that would still be very nice is to reach a strong coupling limit of charge and possibly also spin in these semiconductor nanostructures. And I think there's ways how to get that working, and that's one of the things that we look at our lab. And once you have it working, then you can use these resonators as coupling buses for semiconductor-based quantum information processing, and that's something that actually a number of groups also look at. Okay, so with that, I'd like to thank you for your attention and apologize a bit for my bad timing, but I think it was good.
So, you consider the photon emission of certain double dots, but phonon interaction is much stronger. Than to emit a photon. So nuclear will emit phonons and photons.
That's true, yeah. So I think one version of this experiment that we would like to do is, I think an interesting question is to determine this branching ratio for, so to know exactly what fraction of decay or what part of the energy gets relaxed by phonon emission and what gets relaxed by photon emission. And one of the reasons for the small efficiency which we measure is actually this phonon decay channel, which we don't look at because we currently can't detect the phonons. Yeah? And so an interesting experiment that we'd like to look at is to put this also into a structure that controls the phonon spectrum and see what we can learn from this. The other reason why the efficiency currently is so bad is also, or why this conversion efficiency seems to have a so small branching ratio into the photons, is also that the cavity line width is still small in comparison to the dephasing rate. Yeah? So even if you were able to emit a photon, you'll more likely, because it's not resonant, that process will not happen. And even though that the phonon emission might happen at a slower rate, you might still preferentially emit the phonon because the photon emission is suppressed because it's not resonant. And that would also be interesting if we could improve the coherences and look at that question again. But to definitely do an experiment where you can clearly say, okay, this part is photonic type of excitation, some electronic excitation in your gates or so, or a phonon type excitation in the surface. That would be a very nice experiment to do, like one where you can really measure all these parameters with good enough accuracy.
What intrinsic quality parameters do you get for your cavities?
So gallium arsenide is piezoelectric, and also with Peter, well, maybe he knows more about it now, we try to estimate a bit what one would think the cavity Qs should be on a piezoelectric material for these waveguide structures. And maybe Peter knows more. The best Qs that we typically get on gallium arsenide are maybe like 5,000 or so, 5 to 10,000. So maybe more like 5,000, and that's good enough for this. So it's much better than the line width of the charge state. So at that point, you wouldn't care. If that is something that bothers you, you could also try to make the cavity on a different type of substrate or so. For example, nanowire quantum dot experiments don't suffer from that problem because they then deposit the nanowire on a different type of substrate material.
I understand why there is a shift in the space for your experiment, but what about the amplitude? How do you understand that and how can you model?
Yeah, okay, so the situation that took us a moment in the beginning to understand is this is sort of a somewhat untypical cavity QED limit because the dephasing rate is so large. And so one way how you can relax energy is that your quantum dot picks up an excitation, but then it moves out of resonance of the cavity and then emits it into a phonon, for example. And that will be a loss mechanism that we see, and that loss will actually change the transmission amplitude. And in the end, it's a combination of the loss rate from the dot and the dephasing rate, which is very important in these type of experiments. So it's not only, I mean, it's not lossless. So if it was lossless, you would only see okay, this was measured at fixed. The plots were all displayed at fixed frequency, I guess, the ones that I showed to you. So there's different aspects. So one is just frequency shift in the cavity. So that would be if it was purely dispersive and if loss would not matter. That's probably what you're referring to. So that's one component.
Capacitance, right? Between the dot, the electron is moving back and forth, and you have a change in capacitance, right? So you have like this. This is the way that I understood it. So basically, then after that, to have some kind of loss of
So this was if this was all that was happening if the dot would not introduce an extra relaxation mechanism then you would only see this frequency shift. Yeah? But because the dots create an extra relaxation mechanism, because you can create phonons, for example, you can transfer. So the G is large, so the photon dot coupling is large, and the dot has a large dephasing and a significant energy relaxation rate. Yeah? So you essentially transfer energy from the resonator through the dot into phonons, for example. And so that gives you one of the decay channels, results in this application.
Okay, last question. Yeah.
And so what kind of Purcell factors do these experiments refer to? And the second question, would you expect super radiant features if you put many of these qubits?
With superconducting circuits, there have been super radiant features. Yeah, we've done a sort of 2-qubit super radiant experiment, and that's published, so that you would expect here. And when we think about the Purcell effect, I think when you think about the Purcell effect in the optical domain with semiconductor quantum dots, what you want is a large Purcell factor. You want an enhancement of the emission rate, whereas in superconducting qubits, we usually want a suppression of the emission rate because we want to keep it coherent, and that's probably also what one wants here. I think so what people mostly look for is a sort of a Purcell suppression rather than a Purcell enhancement. And so you were looking for the Purcell suppression or the Purcell enhancement?
No, this experiment for an enhancement. If you look at the emission of the light.
So so here it's limited by this by this dephasing factor. Yeah? Because and since we only can look at those emission processes that happened at the resonator frequency within the bandwidth or within the line width of the resonator. So I think here we get the Purcell enhancement factor relates to this coupling strength. Yeah, the coupling strength is large for us, but the dephasing is even larger. Yeah, so I think if you think about it in this sort of semiconductor optical radiation emission context, the cavity here would not provide a Purcell enhancement, because if you would integrate over the total emitted power from this double dot, yeah, it would be large because most of the power doesn't get emitted into the resonator, and unlikely it gets converted into phonons and partially into photons at frequencies that are not captured by the resonator.
Okay, let's thank Andreas again.